Load. So number 4, a ladder 10 feet long rests against a vertical wall. All right, so that vertical wall is, we're going to assume that vertical is, well, this is going to sound kind of foolish, but we're going to assume that vertical is perpendicular to horizontal. When we talk about contextual situations, we're going to make the assumption that everything is perfectly as they say it is. So when they say that we have a vertical wall, it's perfectly vertical. When they say the bottom slides away from the wall, it's sliding away along the ground, which is perfectly horizontal. So we got to make some assumptions. Not overly practical, but something that we have to live with in order to make this make sense. All right, so I got my ladder. All right, it's leaning against the wall and it's sliding away at a rate of 1 foot per second. All right, so it's moving along. The base, anyway, the base is moving along at a rate of 1 foot per second. All right, now that rate is in the horizontal direction. So this is, we can assume the x-axis and we can assume that this is the y-axis. So this is a horizontal rate of change. So we would call that the rate of change in the x direction per unit of time, dx dt. We would establish that to be 1 foot per second. All right, so 1 foot per second. All right, now it's a question of positive versus negative. All right, I'll get you for attendance. So we have direction, but we also have magnitude. Now, when you're talking about velocity, you're talking about something that is a vector quantity. Right? Vectors have magnitude and direction. So we could look at this and say that on a couple of different levels, that it's going to the right, and the right is typically a positive direction, but it's actually even more pronounced than that. The x value is increasing, right? So if the x value has a location here, they're saying there's going to be a moment in time when it's 6 feet from the wall, but let's say it's 2 feet from the wall at this moment, right? And it's sliding away. I'm not going to write the number 2 there, but I'll just put some sort of indication of some distance here. I'll call it a. All right, but let's say it's 2 feet. All right, 1 second later, it would be 3 feet away. 2 seconds later, it would be 4 feet away, and so on. All right, so the distance is increasing. All right, so that means that the rate of change would have to be positive. All right, rate of change is positive. Because horizontal distance is increasing as time elapses or as time goes on. All right, for positive changes in time, we expect more distance. I mean, there will eventually come a maximum distance that it can achieve. Once it gets to, I mean, it would even happen before 10 feet, but once it gets to a particular moment, the ladder comes down and the length of the ladder would be resting on the ground and it wouldn't be leaning on the wall anymore. But that's besides the point at this juncture. Right. So what we want to know is how fast the top of the ladder is sliding down. All right. So the top of the ladder, as the bottom of the ladder is sliding away from the wall, the top of the ladder is sliding down at some vertical rate of change. And that's what we're looking for. All right. So ultimately, I mean, we need an equation that relates x and y in some capacity. All right. So I'm going to generalize this and call it, instead of that arbitrary value a, I'll call this x, some horizontal distance x, and this distance I'll call it y. And that looks pretty bad. All right. So we know that the ladder itself has a length of 10, and we're assuming that this vertical wall and this ground are perpendicular to one another. So we're looking at a Pythagorean relationship here. All right. They didn't mention anything about any angles. They didn't mention anything about area in any capacity. So the only thing that we would have to address here would be dimensions, and dimensions are Pythagorean because it's a right triangle. So a rule or a formula that I could use would be x squared plus y squared is equal to 10 squared. All right. We don't have to create a variable for the ladder because the ladder's length is not changing. All right. So this is constant. Because the ladder's length is not changing. All right. But now we have an equation. So I can take the derivative implicitly. We're taking the derivative of each of these terms with respect to t. So x squared has a derivative of 2x, but that x is a variable quantity dependent on time. Okay. So, all right, I'll get you folks for attendance. Thank you. All right. So x is a variable quantity dependent on time. And so we would then need to multiply by dx dt. Y is a variable quantity depending on time. It has a different value. So when I take the derivative of y squared, it becomes 2y, but then I'd have to multiply by the derivative of whatever that y function is in terms of time, dy dt, or y prime if you want. The constant is the nice part of it. Derivative of a constant is equal to 0. Constant squared is still a constant, so it still goes to 0. All right, so that part's nice. All right. Now they gave us some information here related to a rate of change. They told us that dx dt is equal to 1. They told us that, or they asked us to find how fast the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet. So if we can assume that this length here is 6 feet, I can start plugging in some numbers. I can say 2 times 6 times dx dt, they told us is 1, plus 2 times, I need the y value, but we can figure that out with the Pythagorean theorem. Also, it just so happens to be a Pythagorean triple. All right, this is kind of like what we call a tailor-made problem, where it's kind of like the numbers are selected just so because they work out really nicely. All right, so if you use the Pythagorean theorem to solve for the missing side, you would get a result of 8, 6, 8, 10 right triangle. It's one of those classic Pythagorean triples. You remember? Well, honestly, I was only trained to remember 3 of them. Right? The 3, 4, 5 right triangle, the 5, 12, 13, and the 8, 15, 17. Right? They sort of drilled that into my head back in the day, and honestly, I haven't regretted it. Right? These are the classic Pythagorean triples. And I got to say, very rarely do I actually have to use the Pythagorean theorem to find the missing side when dealing with fairly clean numbers. It's usually the funky decimals or radicals that I have to do that sort of thing for. Right? So anything that has these, and it looks like it says tripes. There's an L tucked in there. But any multiple of 3, 4, 5, 5, 12, 13, or 8, 15, 17 are also going to be Pythagorean triples. So double 3, 4, 5, you get 6, 8, 10. Right? So you just kind of, if you know those triples, there is a payoff for it. Right? Right? And you know, I might be preaching to the choir. It might be something that you also had drilled into your heads. I mean, that's a pretty graphic way I'm describing it, but that's a metaphor. Right? So 12, plus 16 dy dt is equal to 0. Solve, so I subtract the 12, 16 dy dt is equal to 12, negative 12 dy dt would be equal to negative 12 over 16. So simplify, and so we're looking at, what is that, negative 3/4. So equals negative 3 over 4, 4 quality 3, let me fix that. Rate of change, it's a measure of feet, and the time is measured in seconds, so feet per second. Right, so for every 1 foot that the ladder moves out, it's going to drop 3/4 of a foot. If you want to put it in inches, you can, 12 inches compared to 8 inches. So 8 inches, 9 inches, 3, 6, 9, 12. So that's a pretty classic problem when it comes to related rates. It happens frequently. That problem, I mean, you'll see, you go through textbooks, online resources, whatever, you'll see variation after variation of that particular type of problem. Maybe a little twist on it here and there, but it's essentially the same thing over and over again. Seem to like, when it comes to application questions for calculus, we seem to like boxes that have no top and ladders sliding down walls for some reason. They just keep coming up over and over again. Number 5, the altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area of the triangle is increasing at a rate of 2 square centimeters per minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 centimeters squared? Okay, so you think about a formula that might make sense here. They're talking about altitude. Another word for altitude is height or depth. Talking about area of a triangle. I mean, you could draw the triangle, but area of a triangle formula is something that also is probably ingrained mathematically at this point. Area of a triangle, one variation of the formula is 1/2 base times the height. Base times height over 2. Right? There's a trig version of that when it's not a right triangle, but when they say an altitude of a right triangle, the altitude always intersects the base, forming a right angle. Right? So it forms a right triangle. Right? So the altitude we would refer to as the h value. Right? So altitude is h for height. It's increasing at a rate of 1 centimeter per minute, so that's a dh dt, rate of change of the altitude per unit of change in time, while the area is changing at a rate of 2 square centimeters. So that's a dA dt, A for area, so capital A. That is. Let me just get an underline going here. So dA dt, I don't know why I was about to write it too. No excuse for that. At what rate is the base changing? So the base is B, rate, talking about a derivative. So they're asking us for dB dt. All right, so they gave us 2 rates and we're looking for a third one. All right, I see 3 variables in my formula here, which tells me that I shouldn't, it's not like the cone question, I shouldn't be looking to swap one of these variables out. I want to actually keep all 3 of them because I know 2 of them and I want to find the third one. All right. So they also give us some metrics related to the actual lengths of these sides, but let's actually get into the derivative process. These are all variable quantities, all right? So if we have an altitude increasing in a triangle, it would stand to reason, and also the base, it would stand to reason that the area is also going to change. So if 2 dimensions of a triangle changes, overall area is going to change as well. Right? So in terms of making a Desmos out of that, it's very doable. I just don't know that I want to do it right now. I'll do it after the problem, just so I don't kind of ruin the flow here. So derivative of each part of this, well, I have a product of two variable functions here, so I'll have to apply the product rule there. What I'm going to do, and this is a choice, is I'm going to group the 1/2 with the b. And make this the pair of factors that we'll use in the product. All right, the derivative of a is just going to be dA dt. So I'm going to apply the product rule here. We knew that was going to come back at some point. So I have my two components. The first times the derivative of the second dh dt. Plus the second, h, times the derivative of the first. By the power rule, that becomes 1/2 b to the 0th power, just 1/2. But then since b is a variable function in terms of time, I have to then multiply by dB dt. All right. So let me just get my highlighter going there. So then I would just start plugging and chugging away, but you'll see here that we don't quite have enough information to finish up the problem, but we're pretty close. We just have to do one, we have to take one little side quest here. All right, they tell us that dA dt is equal to 2 square centimeters per minute. They don't tell us the base. They tell us dH dt is increasing at 1 centimeter per minute. Increasing means positive. If they said it was decreasing, I'd make it a negative number, but they didn't. All right. They said that we care about this when the altitude is 10 centimeters. We're asked to determine what dB dt is, so I have nothing to plug in there, but I don't know what b is. But they gave us another piece of information we just haven't accounted for yet. That's the fact that the area is 100 square centimeters. All right, so you look at that and say, all right, perhaps I can use that to figure out the base. Right, it's not the value of the base, but it'll help me figure out the base because we do know the area is 1/2 the base times the height. They gave me the area and they gave me the height. All right, so 100 is equal to 5b, making b equal to 20. So indirectly, they gave us the base. We just had to take the time to figure it out. So I pop in a 20 there, and we're looking at 2 is equal to 10 plus 5 times dB dt. So then I'd subtract, I get -8 is equal to 5 dB dt. So divide by 5, and we're looking at dB dt is equal to -8 fifths. That's actually telling us it's getting smaller. You know, may or may not be expected. You know, sometimes it's something other than what you would expect that happens, but you know, okay, so it's getting smaller. That means the base is actually closing in. Right, that's fine. But the units, the base is measured in the same units that the altitude is. Right, so centimeters. And time is measured in the same units as every other rate that was given, which would be minutes. All right. So there it is. Now, in terms of creating a diagram for this, it can be a little funky, but Desmos can handle it. Just you got to understand what the parameters are going into the problem. So you need to have an idea of what's happening. Well, first off, again, the altitude was given, it's a variable altitude. It's going to increase, decrease, but at some point it's going to be 10. Right? The base is going to increase or decrease depending on movement of a point, but at some point it's going to have a value of 20. So it'll be it'll be wider than it is tall. So I could actually just kind of modify this here. And so you'd have a triangle that looks something like this, with the dimension here of 20, dimension here of 10, and then we knew that the area at that moment would be 100. Right? So what we would want to do is create sliders to allow this point to move around and this point to move around. But this point, at the vertex angle, the right angle, we'd want that to stay fixed, right? Because we want it to remain a right triangle. Right? So that should be pretty easy, because what we could do is plot some points using the table approach. We would need some coordinates, but those coordinates are easy. We just put in like A equals 0, something like that. Create a slider. Do the same thing for like B equals 0. Right, just to get some values in there. Now I want to have 0, 0 as a point. I want to have some point on the y-axis, and I want to have some point on the x-axis, and I want them all to be connected. Right, so I'd create a table. 0, 0 would be 1 point. I want a point on the y-axis. Any point on the y-axis has an x value of 0 and a y value that's generally not 0. Right, so I'll use A because I have a slider for A. Now it plots it at 0, 0 because A is set to 0, but if I move my A slider, it'll move it up. Right. Now what I would do is I just long press on this. I don't know why it does that shading crap, but it does. Right, turn on the line and it'll create a little line segment. Make it a little thicker. Oh, I hit the wrong thing. Make it a little thicker so you can see it. Although touchscreens are not the most conducive for Desmos, but it works in some capacity. All right. So then another table. Move this down. Another table for a point on the x-axis. So I want 0, 0. And I want B 0. Right? Because any point on the x-axis would have a y value of 0, but an x value of something other than 0. All right, so I could slide my B over to verify that that's actually giving me a point on the x-axis and only on the x-axis. All right, so I can vary my length. Now I want my length to go out to at least 20, so I can change my slider here to go up to, I can make it 20, 30, whatever. I'll make it go to 30. And I want my A slider to go at least as high as 10, so maybe I'll make that go to 20 so I get a little room on the high side. Right, so long press on the scatter plot, turn the line on, and again, make it thicker if you want. But I'm having enough trouble to make it actually exist to begin with, so that's kind of troublesome. All right, so then you have that. Now I want to have my 2 points making the hypotenuse connect. So my 2 points, my 2 relevant points are 0A and B0. So 0A, B0. Again, I need a line segment connecting those. It'll let me. And there we go. We have a triangle, decent looking triangle there. Now, if I change my dimensions here, I can actually illustrate the movement showing the height or the base increasing or decreasing and the height increasing or decreasing. right? And so you can actually kind of start to get an idea of what's happening with the triangle as one increases and the other doesn't. The one thing that you kind of run into here is the fact that we don't know what the area is, and that can be a little tricky, right? Well, what we want is to have kind of like a running calculation of the area so we get a sense of what's happening in terms of the rate of change of area, right? So that could be a separate calculation where you say A is equal to A for area half the base value. Well, I use the B to represent the length of the base. So half times B, and I used A to represent the height. I could have used H now retroactively. I kind of wish I did, but now I can get a sense of what the area would be depending on different values. And so I slide this slider over to 20, if it'll let me, this one over to 10, and I go down to my area and I see it's 100. And so this is really what the figure would look like under those circumstances. Okay. And just like everything else, I'll save the Desmos for you because this is the kind of thing that I think it helps in terms of visualizing what's happening, because we could all get questions right. You follow steps, you plug into a formula, you take derivatives. But if you want to truly develop an understanding of what's actually physically happening, having a nice interactive diagram goes a long way. Black and that. Exactly. So I'll save this. I don't even know what to call it. Related rates. Area of a triangle. All right, so at least you have that. And honestly, you might find yourself not ever using this in this class, but maybe you find yourself in a Calc 2, Calc 3 class, you need a visual for something. Or maybe for some other purpose, you just need to have a triangle that you can manipulate the lengths. You could also figure, okay, well, I don't need it for a triangle, but I need it for a square or a rectangle or something along those, a pentagon. You can modify this and kind of use this as a framework. Just something anyway. Hopefully it's helpful. And I like to think. Anyway, there's a bunch of other problems that follow. They're not all riveting, I guess is the right word. Some of them are a little bit in the kind of like redundant, tedious sort of vein, but some of them I think are kind of interesting, right? So, or at least you could find value in what the applications of this would be, right? So let's take a look at number 5. Where it says the volume of a tree is given by this formula. Right? So, I mean, it's kind of a pretty perfectly, a pretty perfect tree in the sense that you can model it with an actual function. Right? C is the circumference of the tree in meters at ground level, and H is the height of the tree in meters. Both C and H are functions of time in years. Right? So part A is just saying, find a formula dV dt, which is really just saying, take the derivative of the thing that they gave us. Right? Now, as nasty as this might look, it's still a product rule situation. Right? So I'm going to group the 1/2 c squared together and the h all by itself by choice. Right? If I wanted to, I could have grouped the 1/2 up 1/2. I keep saying that the wrong thing, and I just kind of hope it makes sense. The 1/12 pi, I'm choosing to group that with the c squared, but I could have just as easily kept the c squared alone and grouped the 1/12 pi with the h. Multiplication is commutative. I could do it in any order I want. And this is the order I choose to do it in. All right. So I got my two factors. I'm taking the derivative of this with respect to t. So dv dt. And again, they tell us that c and h are functions of time. All right, so they're variable. They're not constant functions. All right, so I take my derivative using the power rule. So 2 over 12 pi would become pi over 1 over 6 pi, c to the first power, but since c is a variable function, I would multiply by dc dt. Right? It's weird that I did that first. I have no idea why I did. Hold that thought. There, I got my wires crossed. I apologize. First times the derivative of the second. Derivative of the second is going to be the derivative of h, which is dh dt. Plus the second h times the derivative of the first, which is the thing that I figured out first for some reason. I'm only able to chalk that up to it's late in the week, and it's the time of year where everybody's exhausted. Days are starting to get shorter. That's my excuse anyway. That's what I'm doing. All right. So what does it represent in practical terms? Right. So, I mean, it's really just a matter of the units, really. It really. If you think about it, it's saying the volume is given as this. That's great. But dv dt is really the rate of change of volume per unit of change in time. All right. Well, the units of time are years. Right. So if volume is talking about the size of the tree, volume of a tree is a measure of the size of the tree. You know, when you think about volume in a science class, they talk about like matter, mass, things like that, and then you get into volume. And definition of matter is has mass and takes up space or something like that, if I remember correctly, right? But the volume part is the amount of space an object takes up. So the more volume it has, most likely, the more space it takes up, right? So if it takes up more space, it's probably bigger. So it's reasonable to assume that the volume of something gives us an indication of the size of that something, right? So what dv dt is giving us is the rate of change of the size of the tree. Now, it's not talking about height specifically or width or anything. It's just the overall space that the tree takes up per unit of time. So this is giving us a measure of the change in size of the tree per year. Because what I mentioned was it's per unit of change in time, but time is measured in years. So per unit of change in years, how about per year? All right. If I say, how fast is that human's height changing per unit of change in time, where time is measured in years, it's pretty much the same as saying, on average, how much taller do you get every year? And so that's what we're saying. How much bigger does that tree get every year? Does it get a little bit bigger? Does it get a lot of bit bigger? Like how does that work? Can we expect a tiny little seedling to become a full-blown evergreen by the following year, or is it like just going to be a little bit bigger? What are we talking about? That's what this is giving us, right? Which is kind of cool when you think about it. It's a nice application, right? So if you're able to come up with a function that actually tells the size of an object over time, then that becomes a predictive model. But not only will it tell you what the size is down the line, it'll give you a sense of how fast that object is growing. Now, if that object happens to be the amount of money that you have in a bank account, though it's more of a like a virtual object rather than a physical one, it still is going to give you that result, because volume could be the amount, the amount of space your money takes up, right? AKA how much money you have, right? So rate of change of money over time, that sounds like a pretty important piece of information, right? So we're talking about a tree here, but it really could apply to anything that has a growth aspect to it, right? So suppose the circumference grows at a rate, circumference of C grows at a rate of 0.2 meters per year. So dc dt is 0.2 meters per year. Just make sure there's no funny business when it comes to the units. I won't do that to you on the test, but when you go to practice problems on your own, you find some problems online or something like that, I find that a lot of people mess around with the units, and they'll be like, the rate of change is blank centimeters per year, but the original problem is given in meters and years, and you have to do a unit conversion. So just be careful about little things like that. Take note of what units were given and what units they're asking you to represent your answer. All right, so 0.2 meters per year, and the height grows at a rate of 4 meters per year. So the HDT, 4 meters per year. How fast is the volume of the tree growing or changing or increasing, decreasing, depending? When the circumference is 5 meters and the height is 22 meters. All right. So this part of the problem is actually pretty easy, because if you look at what we figured out in our derivative, provided we take the derivative correctly, which is, that's a big ask, but sometimes, and sometimes you make a little mistake here and there, but most of the time, if you're careful in taking your derivative, you're not looking at too much trouble the rest of the way. So 1 over 12 pi times 5 squared times 22, all the units are consistent. So I'm just running through and changing and plugging in numbers. Sorry, the HDT was 4 plus 22 times 1 over 6 pi times C, which is 5, times dc dt, which is 0.2. All right. 0.2 is the same as 1/5. 1/5 of 5 is 1, so these cancel out. All right. So 25, 5 squared is 25, times 4 is 100. So 100 over 12 pi plus, well, this would be 22 over 6 pi. I mean, that's fine. I can just pop that in if I want. But 22 over 6 pi, if I get a common denominator, would be 44 over 6 pi. 44 over 6 pi. 44 over 12 pi, hence the common denominator. All right, so 144 over 12 pi. And it's at this moment that you realize that this must be a fictitious problem, because there's no way real life works out this cleanly. 12 goes into 144 12 times, so 12 over pi. And we're talking about a rate of change of volume. Volume is cubic linear units, so cubic meters per unit of time, because it's a rate of change in terms of years, so cubic meters per year. All right. Now, if you wanted to do this on a calculator, you could. Just be prepared to represent your answer in terms of pi, because it's cleaner that way. All right. So if that's the case, just factor out a pi, do all the other computations, and then multiply by pi later on. This way you don't run the risk of the calculator.
Professor, can you scroll down a little bit?
That way?
Like the other way. Thank you.
Yeah, no problem. So that's the concept of related rates. There's some problems that we skipped over, but I think those are good for practice. And so what I'll do is I'll just kind of table those till next time, because, I could go over them all, but if I do, at least before you have a chance to try them yourself, I'm doing all the thinking for you, and it doesn't give you an opportunity to kind of try to do the thinking yourself, either succeed or not succeed, and then learn from the experience. So yeah, we'll table those to next time, but we will go over them. It's just a question of when. Right? But we're going to move on to the extreme value theorem and different applications of the derivative involving what's known as optimization. Right? So also pretty interesting applications, but they're all kind of academic in the sense that if you have a model, a function model that you can use to represent a situation, then it's very easy to do the calculus to it, if that's any kind of grammar. But if you don't have a function model, then you end up having to collect data, analyze the data, regress the data to come up with the function model, which is why we did the technology assignment, showing that you could have some nasty functions, and those nasty functions can give you meaningful results. Right? But we need to get to a point eventually where we're going to do some data collection to create the functions to begin with, where those functions could then be analyzed using calculus. Right? But before we do that, we get the skills. Before we get to the fun stuff, we go through I don't want to say the boring stuff, but it's more like the procedural stuff. Right? So the extreme value theorem is telling us that if you, I mean, I can read the blurb here, but it's basically saying that if you have some kind of closed interval, meaning bookends to your function, a restricted domain, and along that domain, there is a smooth continuous function, then that function has to have a maximum or a minimum somewhere along the lines. Right? So it's just a question of what kind of maximum or minimum. Right? They could be what's known as relative extrema, relative maximum, relative minimum, or they could be absolute extreme. Right? So the difference between the two is actually pretty significant. So let me just draw a quick sketch for you here. This is my classic Extrema sketch. I got to make it my classic Extrema sketch. It's just, I have such shaky handwriting these days that it never comes out right the first 7 or 8 tries. All right, I'm just going to go with this. It's not my classic one, but it'll get the job. The classic one had a couple more dips and turns along the way. All right. So here's some arbitrary function that we call f of x. All right. Along the way here on this f of x, we have little peaks and valleys. All right. Those little peaks and valleys each have high points and low points. All right. Those high points, while not being the highest point overall in the entire function, because this function goes up to infinity and down to negative infinity, these points are higher than the points that immediately surround it. Okay, so just on this little interval here, just on this little area here, and just for this little area here, we have little peaks and valleys where there is what we call relative extrema, or relative max, relative maximum, relative minimum values along those little teensy tiny intervals. All right. So each one of these high points are what we call a relative or a local maximum. And each one of these or what we call a relative or a local minimum. Okay. So they're not the highest and lowest points on the graph overall. They're just higher and lower than the points that immediately surround. Right. Now, if I take my graph, I'm just going to shrink it down a little bit. If I take my graph and follow it to its natural conclusion, this one would go all the way up to positive infinity. A different color there. And this one would go all the way down to negative infinity. So there is no absolute maximum, right? In the sense that we never get to an overall highest point because it always increases forever and ever without bound, right? Now, if I were to make a little turn here, so a little adjustment, right? So I have this curve here, and then I get to this location here, and let's say I have another turning point. See, that's the problem with nerve damage. It sucks. Let's say it veers off. All right, pretend that's picture perfect. Oh, now it is because, I didn't do it. Right, but that's all right. I just want it to be a little bit higher. All right. So let's say it goes down forever. So this is gone, no longer exists. Right. So this is irrelevant. Right. So you could just pretend it's not even there. I'll just move it off to the side for a second. The difference here is now what we have is a graph that actually does have an absolute maximum, right? Because it doesn't go all the way up to positive infinity. It actually stops right here before turning around on itself, right? So this would actually be a couple of things. It would be the absolute max. It would also be a relative max, right? Relative or local max, right? So the reason why it would be relative is because it still satisfies the definition of a relative maximum where it's higher than the points that immediately surround it. Right? It also happens to be the highest overall point in terms of y on your graph. Right? So you have a lot of different situations that we got to be mindful of. One is that maybe there is no absolute max, like my original diagram before I modified it, but maybe there is, and it's a fixed point. What we need to learn how to do is identify the difference between the two just by looking at the equation, right? But looking at the equation, quote unquote, looking at the equation really means doing calculus to the function, right? So let me get rid of this. And we'll dive right into that. Now there's some notation heavy stuff that you see below. The Extrema, like all that stuff. It really is just talking about the things that I just discussed, right? It's just very mathy, right? I'll get into the notation heavy variations of it, but I wanted to talk to you about more of the intuitive understanding before we get into it. Right. So we have the process there. Honestly, I got to read this process because I wrote it such a long time ago and I've made so many edits over time that I can't remember if this is the version that I didn't like and I edited or didn't like and I forgot to edit. Let me see. Find the first derivative, plug the x value of the coordinate of the relative min max software. Yeah, no, this is crap. All right, so this is a typo. It's like a really big one in the sense that it doesn't really tell you anything. All right, I'll show you the technique. Yeah, I don't honestly, I don't even remember where I got this from. I think I got it from like a website like 20 years ago, and I just never changed it. All right, so that process is no good. All right, when you're looking for, and honestly, one of the reasons why it's no good is it doesn't tell you what you're looking for. All right, so first we need to identify what are known as critical values. All right, so in order to find a critical value, that's going to involve something called I don't even know where I was going with that. Critical values involve derivatives, right? So, but it'll involve left-hand and right-hand side derivatives. So we'll get into that in a minute. But to find critical values, set the derivative equal to 0 and solve. Set the derivative equal to 1 over 0 and solve. All right. Those are ways in which we can determine the critical values, right? And then those critical values in turn could be, not guaranteed, but could be relative extrema. So, and I'll get into why we do that in a minute, but let's look at these examples. There's for each visually determine any relative extrema and then determine a derivative at each relative extremum, right? So this is actually going to give us a kind of an avenue into understanding why this works the way it does, right? So first off, I want to kind of address continuity, right? So looking at this graph, you know, it's not a pretty graph, and actually I'll even take that as a typo because these are old like ugly TI-84 graphs. Like that's not nice. I'll get a good looking one here. I'll get the grid off. We don't really need that. It's just y equals, or f of x equals the absolute x. Yeah, that's a good looking graph right there. But it looks exactly the same. Yeah, you know, it's a little bit crisper, you know. So regardless, we're looking at this over the interval of -2 to 2. All right. This function is continuous on the interval of -2 to 2. So we're going to keep that in mind. You actually don't even need to write that as long as you're aware of it, right? And just a quick reminder, if you want a restricted domain on Desmos, open squiggly brackets. This applies in your tech assignment also, so it's kind of worth talking about. Open the squiggly bracket in that little keyboard if you're using a touchscreen or just a regular keyboard, you know, shift square bracket. And then just type in your domain, in this case, -2 to 2. All right, but this is what we're talking about in terms of the graph. So I only care about this interval. All right. So they're asking us to visually determine any relative extrema. So relative extrema, again, I mentioned this before, it's a point that's higher or lower than the points that immediately surround it. An end point can never be a relative extremum, right? Because there are points to its right, but there are no points to its left. It has to be surrounded by points, all right? Meaning it's got to have points to the left and to the right, right? Same deal on this side. We would not call this a relative extremum, right? If anything, it's an absolute extremum because it's the highest point on the graph. It didn't ask for that, right? Now, this point down here is a point that's below, if you're comparing y values, because when you're talking about relative extrema, you're comparing y values. Look at all the y values that you see here. That y value at that vertex is smaller than every single one of these, right? The y value at that vertex is smaller than every one of these y values as well, right? Which means that we are, in fact, looking at a relative min here. All right. Now, they say determine the derivative at each relative extremum. All right. Well, there's only one, so we're in good shape. All right. So derivative of an absolute value function, you're like, oh, crap, how did we do that? We didn't cover that. That wasn't in one. Well, we know how to write the equation of a line, and an absolute value function is the equation of a line, just two separate lines pieced together. Pieced together as in piecewise. All right. So why we reviewed that in the first unit. So f of x needs to be modified so that it's no longer an absolute function. We have to write it as a piecewise function in order to differentiate. All right. So first thing I would look at is the slope. All right. Now, change in y over change in x, pretty easy. Count boxes. On this end, we're going down to right to get from the endpoint to the origin. That's a slope of -1. Y-intercept is 0, so negative x, so -1x plus 0, or just negative x. Now, the relevant interval here goes from an x value of -2. So if -2 is less than or equal to x, right, because there's a solid point there, it's allowed to be in the set, all the way up to an x value of 0. All right. Now, the right piece, same idea, the slope here, change in y over change in x, a +2 over a +2. If you go, roll over a little bit. So we're increasing our y value by 2, we're increasing our x value by 2. So it's a slope of 1, so 1x plus 0, or just x. If, now here's the tricky part, because you kind of have to sort of know where the story ends in order to restrict the domain appropriately. If we were just writing the piecewise function for the sake of it, I would say, all right, well, this one has a solid point at 0 and a solid point at 2. So 0, 2, x, let's make some less than or equals in there and call it a day. The problem is, when we go to take the derivative of this, we're going to have an issue with the vertical line test if we don't make one of these exclusive. All right, one of them should include the 0 and the other one should exclude the 0. All right, it doesn't matter which is which, as long as they don't both include the 0, then you're fine. All right, it's just one of those quirks when it comes to the differentiation process that everything kind of falls apart. So we just got to be careful about that. Doesn't matter what order you go in. If we made this one the less than and this one the less than or equal, that would have been fine. Either way, as long as they both don't have equal signs up. Right? And I'll show you in a sec why that works the way it does. Right? When we take the derivative, f prime of x, we take the derivative a piece at a time. So I'd say, well, what's the derivative of negative x? That would be -1. What's the derivative of positive x? That would be +1. Right? So, and again, if this, if that, you know. -2 is less than or equal to x, which is less than or equal to 0. If 0 is less than x, which is less than or equal to 2. Right, so I just took the derivative of each piece separately. Right, writing the piecewise was the important thing, because once you did that, everything else is pretty easy. All right, but let me rewrite this absolute value function as two separate piecewise functions. So y equals -x, going from, well, two separate piecewise functions, two separate pieces of a piecewise function, going from -2 to 0. Y equals +x, going from 0 to 2. All right, so verifying that the two pieces do in fact make up the same function. Kind of important, I would think. We want to make sure we're doing it right. Okay. Now, when we take the derivative, I could type in f prime of x. All right. I type in f prime of x, and you see two horizontal lines show up. One of them is at -1, and the other is at a y value of +1. So this function, this equation is y equals -1, and this one's y equals +1. Right, now you see in both cases it says undefined, and that's because the calculator, Desmos, doesn't understand which one we decided over here was going to be the less than and which one was going to be the less than or equal. So it assumed that both of them were less than, right, and just acted accordingly, right? But it didn't know. So it's saying, all right, well, I'm just going to put open circles at both of them because, you know, you didn't tell me, even though we did, but it's confused, right? So we're responsible for that. But I'm going to turn off my original functions here. Just looking at the derivative here, they're saying what is the derivative at each of these relative extrema? If I look for the derivative at 0, at the x value of 0, this is the derivative graph, right? If I look for the derivative at 0, I got a problem here because one side says it's -1, the other side says it's +1, right? So what we would do here is identify, based on limits, whether or not the derivative really even exists at that location, right? So what I would say is the limit as x approaches 0 from the left of my derivative, and the limit as x approaches 0 from the right of my derivative. From the left, my limit is approaching, I mean, it's not really approaching anything, it's already there. But it would have a value of -1. From the right, again, it's not approaching anything, it already has a value. If it ever got to this location, that would be great. It doesn't, but that location that it's aiming for has a y value of +1. So these two limits are not equal to one another, right? Which means, and this is probably, I would say, one of the more kind of confusing would be the right word. It's one of the weirder situations, but these are not equal to one another. So we have an inconsistency when it comes to the derivative, right? Depending on which direction you come in at, you're getting a different derivative. You're getting a different value. It's non-variable in both cases, right? It's constant in both cases. So what this is actually telling us is that the derivative does not exist at x equals 0, right? Because we have a contradiction. One side says it's -1, the other side says it's +1, right? And because of that, we would say the derivative does not exist. However, and you look at that and you say, maybe, well, that's kind of like disappointing. You know, after all that work, we get a DNE, but it actually, it's a good thing. Believe it or not, it's a good thing. It's telling us that if we get a derivative that does not exist at a particular point, it's telling us, hey, that could be a relative extremum, right? As in an absolute value function, right? So that's kind of interesting when you think about it that way, right? You don't look at it as like, this is the answer. You look at this as, this is the key indicator of whether or not you have a relative extremum, right? Now, that's actually the hardest type of situation. You know, you're given a graph, you have to come up with a piecewise and then find a derivative. And who's to say the piecewise is even going to be this easy, quote unquote easy? You know, like there's a lot of funk going on here, but it's really once you get used to it, it's not that bad. All right. But number two, along the same lines, we're gonna apply some limits here, you'll see. But I can tell you that I don't see a relative extremum there at all. All right. So the question is, how does the limit relate to finding a relative extremum? The limit was finding the derivative at the relative extremum. Right. So here we're looking at, in the instructions, visually determine any relative extremum, then determine the derivative at each relative extremum. All right, determine the derivative at each relative extremum. So that's what this whole process told us to do, or led us to. And so what we determined was that in this situation, when you have an absolute value function, guess what? The derivative doesn't exist at the turning point, at the relative extremum. So if you're given a function, now you just kind of look at it the other way. If you're given a function and that function has a derivative that does not exist, like you do some computations and do some crunching of numbers, you plug some values into a derivative and you get a DNE, you say, oh, wait, I remember that one time that meant that there was a relative extremum there, right? So it's really kind of the reverse. We're taking this answer and using it as a springboard to answer other questions. And also, you kind of look at it and say, well, wait a minute, maybe there's something to do with the fact that this graph comes to a point. I wonder if that has something to do with whether, you know, the fact that there is no derivative at that location. And spoiler, that's exactly what happens, right? But yeah, for the next one, there is no relative extremum. No relative extrema, extrema being the plural of extremum, right? So I don't see any of them. I don't see a point that's higher or lower than the points that immediately surround it. So yeah, you would think, well, there's nothing to do here. Well, there kind of really isn't anything to do, because visually determine any relative extrema. I didn't find any. Then determine the derivative at each relative extremum. Well, there's nothing to do there. Right? So that would be the end of it. All right. If you're not sure, again, we're given the function. I'll just type it in as y equals 1 over x. I'm not looking at anything resembling a turning point. This little curve here, any point along this curve, yeah, it's consistently, as you go to the right, getting smaller and smaller, but there's never a point where it turns around and gets larger and larger. All right. So extrema, turning points, synonymous. You want to think of them as the same thing. So this one doesn't have any relative extrema. You could find the derivative, but even so, you kind of look at it and say, well, what would be the benefit, right? I can tell you that if you found the derivative, there would be some locations where the derivative's not, that derivative does not exist, but they happen to coincide with locations in which the function itself doesn't exist, so it becomes irrelevant. But let me show you one that works out kind of nicely. So we have a relative min. All right. This is on the interval of -1 to 2. So not including the -1, not including the 2, but that doesn't matter because this is at 0 anyway. F prime of x would just be 2x. This has an x value of 0. So f prime of 0, 2 times 0 results in a 0. So we have a derivative that's equal to 0 at a relative extremum, right? That's where these instructions become more clarified, I guess. When I said to find critical values. Now, if I tell you critical values, again, I mentioned this before, but I'll say it again. If I say critical values are numbers that could represent turning points or relative extrema. And the process we use to find those critical values are to set the derivative equal to 0 and solve. That's justified by this computation because we just showed that there's at least one instance where when we take a derivative and plug in the x value at an extreme value, x value at an extreme or relative extrema, the result is equal to 0. So why couldn't we go the other way? You know, if I know the function, the derivative function is equal to 2x, and I'm looking for the x without looking at the graph, looking for the x that leads to a turning point, I could just set it equal to 0 and solve, and that would give me the x. The other part of it is setting the derivative equal to 1 over 0. That corresponds with that first example where the derivative didn't exist or was undefined. Now that's kind of loosey-goosey with the facts a little bit, because this was the case where in number 1, the derivative just flat out didn't exist, but another way a derivative may not exist is if it's undefined, right? So these are good strategies to start you off in the process of finding extreme values, right? So, you know, like maybe we're onto something. I mean, we are, because that's the process. But if I look at this, I see a relative max at x equals 0. And here I see a relative min at, it looks like x equals 2. So I'd find the derivative. (3x squared minus 6x). We'll move it over and shrink it apparently. And then just plug in these values. Values, plural values, with the S on at the end, values. That's the word of the day. Not value, but values. All right, plural of value, that's the word of the day. All right, so 0 gets plugged in. You plug in a 0 for each one of these x's, you're going to get a 0 as a result. Confirms what we suspected. Look at that. Got a result of 0. All right, plug in a 2. 3 times 2 squared minus 6 times 2. 3 times 4, 12 minus 12, 0. We're on a roll. It works out again. Kind of nice. All right. Now, you see number 5 is another case where it comes to a point. So I wonder if there's something funky going on with that one. So I'm going to plug in, we got a relative min here. We'll plug in a 0 to the derivative. Now, we don't really want to beat this to death. You can find the derivative at a point without actually computing the derivative. I mean, I'll write it down here for the sake of writing it down. F prime of x, 2/3 x to the negative 1/3. All well and good. I would plug in my 0. But you could also just type in your function. Right? And remember, I said this a while ago, anything that's numerical in nature in this class is all calculator. Do it all on the calculator, it's perfectly fine. So 2/3, let me get rid of that. I don't know why I opened the print. All right, so that's my graph, good looking graph. I could type in f prime of 0, and it says undefined. Kind of like what I set up here, set the derivative equal to 1 over 0, which is undefined. So in this case, we would get undefined. All right. Now, the next one, the trig function, that's kind of weird because it's like, what am I working with here? You know, like the domain and all that. Well, we know that a sine function, an ordinary sine function has a 2 pi period. You know, your standard, the parent function. So this location here is 2 pi. All right. So if I'm counting out, I could actually verify this very quickly. in Desmos, f of x is equal to sine of x. But I only want to go, well, this is 2 pi, but I have a little bit more graph than just 0 to 2 pi. I mean, I got negative also part of it. But this appears to be a pi. So each little arch seems to be happening in pi unit increments. So it would make sense to say that this is probably 3 pi. So if I'm not sure, I would just restrict my domain on Desmos, negative 3 pi to 3 pi, and see if it gives me the appropriate number of arches. Right? So it looks like it, I mean, the scaling's a little bit different, but we know a sine wave has an amplitude of 1. So I definitely don't need to be going up to 10. Right? So I could change my scale here. Instead of going on the x-axis from negative 17 to 11 and change, I could go negative 3 pi to 3 pi. It accepts it in terms of pi. And then my step, instead of going by whole number of units, well, each little tick mark seems to be worth pi over 2. So I'll type in pi over 2. And then for my y, I really just need to go like a little bit more than -1 in the negative direction, or a little bit less than -1, a little bit more than +1. So I'll go like -1.5 to 1.5. And now I have a pretty good looking representation of that graph. And also, it'll when you change the scale to put it in terms of pi, it'll label it in terms of pi, which is really, I think, a nice feature. Right. So when it comes to identifying these locations, you tap on these points and it's like, oh, this is where it's at. You know, I'll make it a little wider so it's a little easier to see. If you get the scaling right, Desmos will kick out all these values for you and you'll be like, oh, where has this been all my life? / in pre-calc when I had to make all these graphs by hand and all that stuff. Yeah, I remember fighting that battle. It's a tough battle to fight, especially in pre-calc, when you're telling students, no, you'll have to do it all by hand. You got to know the structure of this stuff. And it's like, yeah, you do, but geez, when technology graphs it so nicely, it's kind of hard to say no to it, you know? So you look at that, it's like, oh, look at these readily identified points for us, right? So then when I want to find the derivative, which is easy enough, f prime of x is equal to cosine of x. At these particular points, it's just a matter of popping them in because we know the relative mins and maxes, they're right there in front of us. So it's just a question of how we want to structure it, right? So I could say f prime of x. All right, that'll create the graph, which is great. Now, if you do it at the appropriate locations, you'll just based off the graph, it'll give you the numbers. Now, I found historically interpreting graphs of derivatives have always kind of give students a hard time, but it is very useful if you can, wrap your mind around it. So here's my original function, right? And these are the relevant x values, right? The ones that I highlighted, I put them on the screen over here, right? So if I look at just the derivative function at those same points, all right, at those same locations, it'll evaluate the function for me, right? So I don't care about the turning points of my derivative function. I care about those points at -pi/2, which would be right here. I care about them at -3 pi/2, -5 pi/2, pi/2. Well, maybe not pi/2. feel like I missed one along the way in this diagram here, but you get the idea. I care about these points. Right now, it does get a little messy, but if you keep it straight, it's not bad. That being said, once you recognize the relationship between all of these points here, and again, admittedly, I think I missed this one here. So this would be, what is this, 9 pi over 2? Oh, wait, no, I didn't miss it. It's there. It's just this one is here. This one is here. I confused myself. Sorry about that. You were probably all right. I was the one that messed up. All right. So if I want to evaluate this function and I know that there are pi over 2's built into every one of them, then what I can do is I can modify my derivative. Instead of saying, like, actually typing in -5 pi over 2. All right, that's I got a 0. Great. Now let me do -3 pi over 2. I got a 0 there. All right, that's wonderful. How about a pi over 2 with a slider at a? All right. And let that slider go from your lowest y value, I'm sorry, your lowest coefficient to your highest coefficient. So in this case, -5 to 5. It appears I only care about odd numbers. So let the step go by 2. You can still look at the graph. But now when I do this, I'm looking at the derivative at -5 pi over 2, 0. -3 pi over 2, still 0. -1 pi over 2, still 0. 1 pi over 2, still 0. Still 0. Still 0. All right. And actually, it's kind of nice because I can use this relationship on paper and say the derivative at a pi over 2 is equal to 0, where a belongs to the set of numbers going from -5 to 5 just by odds. You could write them in if you want, or you can use, like interval notation or other kinds of inequality notation or stipulating that they're odd numbers. But you start getting into sequences and stuff like that, it might be a little complicated. So I would just say where a is equal to plus or minus 1, 3, and 5. I think that covers everything. So the notation is kind of nice in the sense that it saves you from having to evaluate by saying f prime of -5 pi over 2 is equal to 0. F prime of -3 pi over 2 is equal to 0. F prime of -pi over 2 is equal to 0, and so on, and so on, and so on. A little shorthand notation goes a long way. All right. So let me just bore you with one more problem. All right. In this case, we're looking at, and honestly, I'm kind of trying to be funny there. Hopefully you don't find this to be boring. I think, like, especially with the technology part of it, it should be kind of eye-opening in the sense that a lot of the stuff that we used to make calculus difficult really isn't much of a hindrance anymore. Right. So we have a relative max at x equals 0. All right. So to take the derivative of this, I mean, it would be kind of a pain, but it's still doable. Right. So, but we don't need to do it. I just need f prime of 0. So again, just pop in your function. I'll just put it in as a g of x. Keep it here. We'll call it g of x is equal to 8 over x squared plus 4. That's my good looking function. Almost looks like a normal distribution, although it's not. If you know what a normal distribution is. If not, take my stat class next semester. I think I'm teaching stat, I'm not sure. But anyway, g prime of x at 0 as a result of 0. If you don't like that, just plug in the 0 and you get a result of 0. All right. So again, numerical cases, you don't need to find the derivative by hand. You just need to be able to come up with the derivative. Right. So the critical values, this is kind of like a this is from the old version. I've already explained this. You can keep these instructions because these instructions aren't too bad. But the examples, you can see they're exactly what we just did. It would be kind of a waste of time, right? So so you can just kind of toss these because it's really the same stuff that we've been doing. Right? So that's another typo for somebody. There's typos for everyone. Typos, hey. But what I'd like you to try to do on page 44 is try to tackle the first two problems. They ask you for absolute extrema, but you can see here that there's a pretty, shockingly, this is a pretty solid step-by-step process. So give it a shot and we'll start off with this next class. Oh, before I forget, critical number, critical value, they mean the same thing, right? So if you ever see that, I use them interchangeably, but sometimes I forget to tell my students that, right? So at this point, and let me just bring back the notes here in case anybody's still writing. At this point, I'm going to stop the recording.